Good morning, everybody. Welcome to the second day of the conference. Nice to see you early in the morning to this not so easy presentation. Let me introduce our two speakers. So Johannes and Caspar work both at the Foundational Research Institute, and Johannes Treutlein researches anthropics and decision theory. And before his work at FRI, Johannes studied the double bass in Stuttgart and Nuremberg and played with the Munich Philharmonic. Caspar studied computer science in the University of Bremen. In middle and high school, he completed a year's worth of university-level courses in mathematics at the University of Hamburg. He has published in the journal Synthesis, and his research areas include theoretical computer science, ethics, and artificial intelligence. I'm very keen to listen to your presentation.
So Caspar Oesterheld and I are doing, among other things, we're doing decision theory research, and especially we're looking at the decision theory of Newcombs problem, which we'll talk about today, and similar problems. Now in this talk, we'll present two papers we're currently working on, and we are very grateful for any feedback or questions that you have. Unfortunately, we don't have the time to take questions during this slot, but please do come to us in person after this talk, and if you have any questions or feedback, and we can discuss them in the break. Now, since this is the kind of advanced track, we will keep our explanations quite short, but we hope the talk will still be intelligible. So I will begin now with talking about the wager for evidential decision theory, and afterwards Caspar will continue with decision theory and approval-directed agents. So, if well-informed and intelligent experts disagree about some matter, then it seems unreasonable for anyone to have 100% credence in any single solution to this problem. And we think this also applies to decision theory. So, there are many different theories that have been proposed, most notably causal decision theory and evidential decision theory. We'll talk about those later as well. And academics can be found endorsing either of these theories. So if you want to say we are uncertain about which is the correct decision theory, we can take this uncertainty into account by using some kind of meta-decision theory. And that's what, for example, Richard Nozick or William McAskill have proposed doing. Now in this talk, I'm going to talk about one implication of using such a meta-decision theory. And that's if we live in a large universe and we care about what happens in other parts of the universe, then this can lead to a wager in favor of evidential decision theory. Now in the talk, for the reason of simplicity, I only talk about causal and evidential decision theory, but this is also a wager in favor of some other non-causal theories, so timeless, logical, updateless, anthropic decision theory. Or also Wolfgang Spohn and Perlinger's variations of CDT. Now, let me begin by recalling a famous thought experiment, Newcombs problem, a variant of this thought experiment. So here we can kind of see what causal decision theory, so CDT, and evidential decision theory, EDT, are about, and this problem sets both of those apart. So imagine there is an omniscient, all-powerful and trustworthy being called Omega, and Omega plays a game with us. So there are two boxes, one translucent box and one opaque box, and we have two options. We can either take both boxes, which is called two-boxing, or we can only take the opaque box, which is called one-boxing. Now, the translucent box contains visibly one wish, and this wish stands for one life saved. So if you take this box, then Omega will save the life of one terminally ill child. The content of the opaque box gets determined as follows. So Omega predicts in advance what we will do. If Omega predicts we would one box, it puts two wishes in this opaque box, which stand for two lives saved. If it predicts we would 2 box, it puts nothing in this box. So here we have an overview over this decision situation, and this table specifies the number of lives saved given either of these two options, and if we perform them in those two possible states, so either the opaque box is filled or it isn't filled. Now there's two ways to reason about this problem, and those two ways correspond to two different versions of expected utility theory. The first one is evidential decision theory, which says we should one box, because one boxing is the action which provides us with the better news. So conditional on observing one boxing, it's much more likely that the opaque box is filled, and that then, because omega is an accurate predictor, and then we'll end up with more lives saved than conditional on 2 boxing. And formally, we can represent this by this expected utility equation, and here we use we sum over the states, and we weigh the states by the probability of these states conditional on our action. Now let's say the predictor is 90% accurate, so a filled opaque box has probability 0.9 conditional on one boxing. So one boxing is action 1 here. And then if we do this calculation, it turns out one boxing is the action with higher expected utility according to evidential decision theory. Now causal decision theory reasons differently. It only looks at the causal effects of our actions. And here, for this reason, causal decision theory would 2 box. So it would think we can't, so the content of these boxes is already determined by omega, and we can't influence the content of these boxes causally anymore. And no matter whether the opaque box is filled or not, in both of these cases, we end up with more money, with more lives saved if we 2 box. And formally, we use this expected utility equation where we use the unconditioned credences in states. Now, this equation doesn't work always, but in the cases we discussed, it works fine. And if we just assume the unconditioned credences are 50% for each of those states, then 2 boxing, so action 2 here, has higher expected utility. Now, as I discussed in the beginning, we might want to use some meta-decision theory because we are uncertain about which of these theories is true. And we can do this the same way we treat empirical uncertainty. So we use expected value approach. And here this dk stands for the decision theories we have credence in, and we just do expected value and weigh all of the values that these decision theories provide by the credence we have in these theories. Now this equation presupposes some things. For example, it presupposes that these decision theories values are comparable and that we normalize them in some way. So I think, at least for evidential and causal decision theory, this is quite plausible, since both of these theories agree in most ordinary cases, and they use exactly the same utility function. So both are versions of expected utility. Only in cases where our action provides us with evidence that doesn't stem from the causal effects of our actions, only in such cases do they disagree. So, and if you use the cases where they agree to normalize them, then we can just give them equal weight, and this is what this equation does. Now let's suppose we have a 90% credence in causal decision theory, since maybe we think more academics are endorsing causal than evidential decision theory, but we have still some uncertainty, so 10% in favor of evidential decision theory. And if we do these calculations, it turns out that 2 boxing here has a higher expected, meta-expected utility. And this also seems not surprising. So since in this case, around equally as much is at stake for causal as for evidential decision theory. And for this reason, because we have a higher credence in causal decision theory, it seems reasonable that here we go with causal decision theory if we use this meta-decision theory. Now, what happens if we try to model this situation in a large universe? So a universe with infinite space is one of the most widely endorsed theories among cosmologists. And if this is true, then at some point in space there will be an exact copy of Earth and an exact copy of our part of cosmos. And there will not only be one copy, but of course there will be infinitely many such copies. Now, since it's hard to calculate with infinities, we just assume here that there's some kind of large number n of copies, and copies of this thought experiment that happen. And furthermore, we also assume that we actually care about what happens in these other parts of the universe. So when some life gets saved, not on this Earth, but on some copy of Earth, this also counts towards our utility. Now, what happens in this situation? Interestingly, the expected utility of evidential decision theory just gets multiplied by this factor. So we don't show here, we spare you the exact calculations. We have proof for this in the paper also. But the reasoning here is that conditional on one-boxing, of course, all our copies will also one-box, and all other omegas in all other parts of this universe will also predict one-boxing, so everyone's going to end up with the same utility, and if you just calculate this towards our own utility, we receive this. Now, importantly, causal decision theory reacts differently to this situation. So the expected utility by causal decision theory just gets shifted by one constant. And the reason here is that we can't causally influence what our copies do. So whatever our estimate is for what happens in these other copies of the universe, this estimate doesn't change according to causal decision theory based on whatever action we take. So the part of our utility function which is determined by our copies is the same for all actions. Now, if we use meta-decision theory in this case, it turns out, and for example we set n to 100 here, then you can see that action 1, so one-boxing, will have a higher meta expected utility. And so this also seems still a kind of desired behavior, because in this case, since there are so many copies and so many lives at stake there, and only evidential decision theory takes the impact that our copies have into account, here we go with evidential decision theory, since much more is at stake for evidential decision theory than for causal decision theory in this scenario. Now, this kind of reasoning from this example can be generalized, and then it leads to a general wager in favor of evidential decision theory. So whenever there's a large universe, so many copies of us, and then if we also care about the gains of our copies. So if as we let this number of copies n increase, the part of our utility function that stands for the gains that these copies get also increases. Then if the universe is very large, the impact of our copies will completely dominate our own impact. And now, because only evidential decision theory takes this impact of our copies into account, only for evidential decision theory this matters, then in fact, whenever we have any non-zero credence in evidential decision theory, we will actually act according to the action that evidential decision theory recommends. So we'll act as if we have 100% credence in evidential decision theory. Now that's, of course, if we use this meta-decision theory in the way I outlined in the beginning. And then this leads to a wager in favor of evidential decision theory, as I said, and of course also in favor of all other theories that take the impact of our copies into account. Now, just some brief words about the relevance that this has. So just in general, this topic is relevant for artificial intelligence or AI safety, since we are here asking ourselves, what's the optimal action we are supposed to perform given some specified goal? And this just generally relevant to AI. Now, there's also some important macro-strategic question that might hinge on this. So whenever there's a kind of prisoner's dilemma type situation, so whenever there's maybe an arms race or some conflict, the dispute between evidential and causal decision theory might matter. And lastly, insofar as this wager pushes us, even if we have a very low credence in evidential decision theory or any non-causal theory, this wager pushes us towards this kind of non-causal reasoning. And so it's also an argument in favor of all other considerations that are based on this non-causal reasoning. So for example, one piece of research by Caspar Oesterheld, which discusses, so the idea here is that based on non-causal reasoning, we should cooperate with other agents in the multiverse or the universe. So insofar as this wager pushes us towards this non-causal reasoning, it's also an argument, even for people endorsing causal decision theory, to take this argument by Caspar Oesterheld into account. Thank you.
Okay, so in this second half of the talk, I would like to talk about the decision theory of approval-directed agents. So within AI safety, there seem to be two questions related to decision theory. The first is, what is the right decision theory for an AI to use? And this is the question that most AI safety researchers who have also thought about decision theory have spent most of their time on. And in a way, it's also what philosophers working on decision theory think about. I mean, they don't talk about AIs in particular, but instrumentally rational agents in general. And I would guess that a lot of that discussion carries over to AIs. The second question, and the question that I would like to talk about now, is the question, how do we implement decision theories, and in particular the right decision theory, in an AI? And although this question includes this word implements, it's still, I guess, in great part a theoretical question. So the reason why this is interesting and non-trivial is that decision theories are usually not, I would guess, explicit in AI architectures. So most AI algorithms don't sort of explicitly spell out which decision theory they use or compute explicit expected values according to causal models or something like that. And instead their decision theoretical behavior is sort of implicit in their algorithm. So one example would be if an AI is based on this paradigm of sort of doing what has worked well in the past, and sort of this paradigm doesn't compute any sort of expected values explicitly, but you can still talk about what decision theories this paradigm would implement. A counterexample for those who know about this is Schmidt-Huber's Gödel machine. So this is an example of an AI model that sort of specifies the decision theory very explicitly, and you can just change the decision theory, and you don't have to change anything else about the AI. And I would guess that most practical AI designs aren't like that, and Schmidt-Huber's Gödel machine is not a practical AI design. Okay, now I'm going to introduce this concept of approval-directed agency. But first, I'm going to introduce the concept of agency. And in particular, we need some model of agency that makes it possible to describe situations in which CDT and EDT disagree. And so this is slightly different from usual models, which just have sort of one probability distribution and provide no way for causal decision theory to provide it, to calculate its causal expected utilities. So we have this agent, and this agent can choose actions, and these actions causally influence the state of the environment. But they can also provide some other kinds of evidence about how the environment looks like. So for example, the environment may contain a predictor who models the agent, and based on what the predictor thinks the agent does, fills boxes with money or not. And so by taking one box, for example, you don't causally change how much money there is in the box, but you gain evidence about how much money there is in the box, or you determine it in some non-causal way. Okay, so much for agency. Now the approval-directed part. So we are going to say that there's an overseer which looks at the agent's action and also partially observes the environment. And based on these observations, it scores the agent's behavior. So it evaluates how well the agent has performed. And the agent's goal is now to just maximize the score that it receives from the overseer. So this approval-directed agent, or this term, is originally due to Paul Cristiano, but I use it slightly differently. So in particular, in Paul Cristiano's model, the overseer doesn't observe the environment at all. And so one reason why this particular model is interesting is that it's sort of a super class of reinforcement learners. So reinforcement learners are agents who maximize what a reward module says, and so the reward module would kind of be like an overseer. Okay, and also I'm only going to look at sort of single decisions because that's just simpler. Okay, one thing that's interesting from a decision theory standpoint about this model is that that basically these two entities together form sort of a new goal-directed agent, and the goal of that agent is basically sort of what is basically the utility function that the overseer estimates. So I'm going to assume that the score of that the overseer gives somehow does something like approximating like how much utility there is in the world, or like something like that. And now these two together sort of maximize this utility function that the overseer estimates. But interestingly, both of these parts of the agent have something like a decision theory. So the agent can use causal or evidential decision theory to maximize what the overseer, which score the overseer calculates, and the overseer doesn't choose actions, but it still has to, if it estimates some utility function, it still has to compute some form of expected value, and it can use either causal or evidential expected value for that. And I mean, causal expected value is sort of a bit awkward in this context because it sort of doesn't properly estimate how much utility there is. But a causal decision theorist might argue that because the overseer's expected value calculations sort of incentivize the agent, it should use causal decision theory to incentivize the agent properly. Okay, so we have these two decision theories, and they're sort of in this single agent. So now the question is, what happens if they're not the same? What happens if, for example, the agent uses causal decision theory to maximize what the overseer, to maximize the score that the overseer calculates, and the overseer calculates the score according to regular conditional expectation, so basically according to EDT's expected value. Well, it turns out the answer to this question depends on what information the overseer bases its expected value calculations on. And I'm only going to look at the extreme cases, which is that either it only bases the information on it only bases the calculation on information that it gets from the environment, or it only bases the calculation on information that it gets from looking at the action of the agent. So first, let's say that it only looks at its observations from the environment, and it doesn't have to look. It may still see what action the agent has decided to take, but it gets so much information from the environment that it doesn't actually have to look at that information to sort of estimate how much utility there is. Okay, so an example, finally. So let's say the agent faces a regular Newcombs problem. So the agent can causally increase its reward or its payoff by $1,000, and not taking these $1,000 correlates with or determines in some acausal way that there's money in the opaque box or in the suitcase or whatever, and like $1 million in the suitcase. After playing this Newcombs problem, Omega will just hand you the suitcase and you can open it and you can see how much money there was, and you will also get the $1,000 and you can look at it, and the overseer can also look at how much money you got. And in this case, it seems that the overseer, to score your performance, just doesn't have to look at your action. It can just look at how much money you won and then sort of reward you basically just for every $1 you get one utilon or something like that. And it doesn't have to think about how your action, whether your action was like a good idea or something like that. It just looks at how much money you got. So this, of course, also means that the overseer doesn't really, or there's no sort of interesting decision theory stuff going on in the overseer anymore, because it doesn't look at your action. It cannot differentiate, there's no difference between sort of causal and evidential expected value. And in this case, sort of the thing that one would expect happens, like if the agent uses causal decision theory, then it 2-boxes, and if it uses evidential decision theory, it 1-boxes. So let's say it uses causal decision theory, then it would reason that by 2-boxing, it can causally increase its reward by $1,000, and with 2-boxing, it can therefore causally increase the reward that the overseer sees by $1,000, and so it can causally increase the score that the overseer calculates by the equivalent of $1,000 in utilons. Okay, so in the other case, the overseer doesn't get any additional relevant information from the environment. It just has to make some guess about how much utility there is based on the agent's action. And now let's take a slight variation of Newcombs' problem. Let's say that instead of just giving you the money, Omega covertly invests the money into increasing your utility function. So, for example, Omega may save some lives, with the money that you won in the Newcombs problem, but it does so in a way that you can't read about it in the news, and you can't observe whether how many lives Omega saved or how much money Omega invested into saving these lives and so on. And the overseer also doesn't see this. So now it turns out that if the agent uses causal decision theory and the overseer uses sort of evidential decision theory's regular conditional expectation, then the agent would actually 2-box, even though it's a causal decision theorist. So it would reason that by 2-boxing, it would, did I say 2-boxes? The agent would 1-box, even though it's a causal decision theorist. So by 1-boxing, it would reason that it sort of causally decreases its sort of actual payoff, how much money it will actually get, by 1,000, but that doesn't really matter. It would reason that by 1-boxing, it can causally influence the overseer to estimate how much money it got or how much utility it got to be higher. So in a way, the causal decision theory agent would sort of think about how it sort of tricks the overseer into thinking that it's got a lot of money, while the agent itself believes that 2-boxing would actually have gotten it the higher payoff. Okay, and what we do in the paper is basically to sort of show that this pattern holds true in general. That is, if the overseer only looks at the world and doesn't receive any additional relevant information from looking at your action, then the agent's decision theory is decisive for how sort of this overall system behaves relative to the utility function that the overseer estimates. And if the overseer only looks at the agent's decision and not at the environment, then the overseer's decision theory is decisive for how the overall system behaves. Thanks.